Hey everyone, my name's Tim Friedhofer, and along with the help of JP Relvis, Lee Krinsky, and Michael Mischison, we're going to introduce all of you to polymer solar cells today. So before we get into the polymers and all that a little later on, I just want to go over a few preliminary things and remind everyone what is a solar cell, or a normal solar cell, and then talk a little bit about how they work. So the solar cell, we know generally what it is. It's some kind of electrical device that's able to take light energy from the sun and convert it into electrical energy that we could use to produce electricity, which can be used to do just about anything. The problem with solar cells themselves is they're not small. They're maybe a foot by a foot, but the amount of electricity that a single cell can produce is very minimal. So a single cell isn't going to be useful to produce a lot of electricity. So what we have to do is hook a bunch of the solar cells up, and we create a solar panel, and then we get a bunch of solar panels. And when we have a bunch of those, then those are the things that you can put on your roof or that you see great big fields of, and that's what produces a lot of more useful electricity. So when we talk about how they work, the general idea that some of you are probably familiar with is that when you have light waves coming from the sun, they travel in forms of a photon, and when one of these photons strikes the surface of a cell, if the photon has enough energy, it'll transfer its kinetic energy to the electron, and then the electron will be removed. If we do that millions and millions of times, then we get a bunch of electrons, and if we could create a flow of those electrons, we'll get a current, which we call electricity. So the phenomenon that makes this all possible is the photoelectric effect. And basically what that says is that when you have electromagnetic waves, and these don't have to just be light waves, they can be X-rays or gamma rays, but those aren't very safe. So any kind of wave in the spectrum is fine. So they travel and they hit a surface, and if they have enough energy and they transfer it to an electron on the surface, then that electron will be removed. So when you look these things up, one of the names that you're probably going to see is Einstein, from everything he did in the early 1900s. And he gets most of the credit because he came up with the idea of the photon, which is the wave particle of how light travels. But earlier on in the 1880s, Hertz was actually one of the first people who did work on the photoelectric effect, but wasn't able to describe it because at the time they had yet to understand what a photon was or really how light waves traveled. So like I said before, the photoelectric effect, it talks about electromagnetic waves in general, but the idea is that in order for one of these electrons to be knocked off the surface, then the photon has to have enough energy. And Einstein quantified that by terming the work function, which talks about the frequency of the waves and Planck's constant. So the photon's energy has to be greater than the work function. And also, like I said, it's obviously possible that we could use any kind of wave to create this flow of electrons, but the sun gives us light waves, so only certain materials will actually use the photoelectric effect from light waves. So once we have this great big flow of electrons, that's nice, but that's not current. We can't do anything with electrons flying around in the air. So what we have to do from that point is we have to create an electric field. And basically the idea there is to get one side that's positive and the other that's negative, and that way we can kind of force the electrons to go where we want them to go. And in solar cells and semiconductors in general, the idea here is to form what's called a p-n junction. And for the p-n junction, P stands for positive, N stands for negative. And the idea here is that the junction, it acts as a diode, which basically only allows electric flow in one direction, which is what we want. So when one of the electrons gets knocked off the surface, then this electric field that we produced forces it to go where all the other electrons are, rather than going back and forth between the positive and the negative side. So once we have all of these electrons where we want them to go, then all we need to do is hook them up to a circuit, and then the electrons will be able to flow where we want them to go.
People have been trying to harness solar energy for a very long time, but doing this using solar cells involving polymers was never the best way to start trying to solve this energy problem. However, there were a number of valiant efforts being made in the early 1900s. The earliest of these attempts involved using anthracene crystals as a semiconducting material, but efficiencies that it produced were almost non-existent and were far lower than 0.1%, which is why these types of technologies were never really used. Professor Ching Tang took the next big step towards polymer solar cell development by developing solar cells that were composed of an anode, a cathode, and sandwiched in between these two things were an acceptor and donor. They could operate at 0.9% efficiencies, and at the time that was unheard of, but unfortunately they still needed expensive vacuum processes to operate, which was not at all desirable since it was very costly. P-type doping inserts small amounts of trivalent impurities into the polymer crystalline structure in order to enhance its electrical properties, and this is done by creating holes through which electron acceptors are created. And an example of a P-type procedure would be to use diborane gas, B2H6, to diffuse boron into a conductive polymer. N-type procedures operate in a similar way, except they use pentavalent impurities instead of the trivalent impurities. And this includes species such as phosphorus and antimony. And this increases the polymer's conductivity by, instead of creating holes, it adds an extra electron that acts as a free electron in the conductive system. And however, N-type doped polymers are known for being less stable than their P-type counterparts, and because of this, the development of these polymers is a little trickier. In the 1970s, three scientists are shown from left to right as Professor Shirakawa, Professor Heeger, and Professor McDiarmid for their work in conductive polymers. They won the Nobel Prize in the year 2000. These polymers have many applications, one of which, of course, is the polymer solar cells that they're used in. And the story started off with the two professors on your right working at the University of Pennsylvania with SNX polymers. And they discovered that these polymers had electrical properties. And then later on, when they gave a talk in Japan, they met Professor Shirakawa, and he discussed some of his work with conductive polymers, and they eventually all worked together towards discovering that if you doped these conductive species with trace amounts of Br or some other halogen, then it could increase their conductivity by 10 million times or more.
So in order for these polymers to absorb sunlight and to create energy, the solar cells need to have a combination of different polymers with varying electrical properties. Since the solar cells need to have both a positive and a negative material in order for the current to transfer, the polymer solar cells use an acceptor and a donor material. Each of these materials are made from a different type of polymer, and using different variations of polymers result in various solar cells with different efficiencies. Therefore, researchers really spend a lot of time experimenting with different polymers combinations in order to maximize the efficiency and minimize the cost. So listed here are some of the most common donor and acceptor materials used for polymer solar cells. Polymer fullerene is the most standard polymer used. It can be paired with multiple different polymer donors in order to create various structured solar cells. Recently, in a lab setting, a group of researchers have found that a new polymer just discovered could increase polymer solar cells up to 15%. This polymer is called PID2. This polymer isn't an acceptor or a donor material, but when it's used in addition to the normal donor and acceptor material, it's able to create a more efficient process for solar cells. This occurs because PID2 allows for electrical charge to move between the donor and acceptor material more easily, allowing for the electrical production of a solar cell to increase.
Now, a solar cell is only as valuable as the amount of solar energy it can convert into electrical power, aka the power efficiency. Besides any output still being better for the environment than any non-renewable resources, it is still necessary to have a reasonable power efficiency. Now, to compare it to non-polymer solar cells usually operate between 11 to 17% efficiency, but have been known to reach up to 40% efficiency in a laboratory setting. Now, early models of these polymer solar cells operated around 4 to 5% efficiency. Fortunately, due to increased interest in technology in this field, it has greatly advanced. Just recently, on February 8, 2016, a company in Germany called Heliotech developed a polymer solar cell that operates around 13.2% power efficiency. This is well within the range of the inorganic solar cells and proves to be vital competition. Heliotech, however, is not the only ones trying to raise the bar. The UCLA research team also recently developed a triple junction polymer cell that reached an efficiency of 11.5%. The idea for this model actually mimics a multi-junction 3-5 semiconductor that is commonly used in space applications. While no issue can be argued more important than another, the efficiency of solar cells have long been a special attention. As an area of focus, the power conversion efficiency is important in order to compete with the more mature silicon technology and also to justify research in the field of polymer solar cells. These accomplishments done by companies and research groups alike indicate that there's definitely strong potential for OPV or organic photovoltaic cells to soon gain the upper hand. The only unanswered question so far is why should we be pursuing polymer solar cells? What are the benefits over non-polymer solar cells? And to answer this, we'll look into a few things. The three largest benefits of polymer solar cells are they are flexible, they are easier to process, and they come at a lower cost. Another very important benefit is that they are independent of scarce resources. Many second-generation solar cells utilize materials that are scarce in nature. With polymer solar cells, this can be avoided. Indium is, however, still used in most polymer solar cells, but demonstrations of indium-free solar cells are still available and in production. Flexibility plays a large role because inorganic cells are for the most part stiff. With flexible thin film photovoltaics, we would be able to apply solar technology in many new scenarios. For example, we could cover curved surfaces now instead of just having those flat, big solar panels. And we could also apply them to small photovoltaic devices. Another example would be good for transportation. With polymer solar cells, we could create large panels, but we'd be able to roll them up, so to speak, and load them onto trucks anywhere easier for transportation. And plastics generally are more lighter, so along with that, flexibility is a major upper hand over inorganic polymer or inorganic cells. Processability is another major selling point of polymer solar cells. Both first and second generation inorganic solar cells depend on vacuum deposition methods requiring massive amounts of energy. However, with polymer-based organic cells, layers are processed from solution. Now, also with this, complete solution processing is a possibility in the near future. This allows for upscaling the production and thus reducing the cost per area of polymer cell. Large rolls of substrate can also be used on which the layers are deposited using printing or coating techniques, which are generally referred to as roll-to-roll coating. The largest challenge of designing polymer solar cells is achieving a design that is both efficient, stable, and could be easily processed at low cost. Like many plastics, polymers tend to degrade in sunlight over time, and as you can imagine, as a solar cell, this is a big problem. And along with this, many methods of designing, when you achieve a solar cell that is very stable, it either comes at a high cost when you process it, or the efficiency goes down, and vice versa. If you if you produce a cell that is very efficient, you may suffer instability. So with future research and more time and funding put into this, we may in the near future achieve a polymer solar cell that has all of these three things, and we may look forward to replacing inorganic solar cells.